Okay, so lesson 6, we're taking a look at the inverse of functions. And let's just take a look first at the definition of a function. Okay, this is just really going to help us with understanding how inverses work. So who remembers what a function is from grade 10? Remember the rules for that? So let's do this. Okay, do you guys remember the test for a function or not? Remember the vertical line test? Yeah, there we go. Okay, so let's say that I have a parabola. We'll say that's one relation, and I'm going to do a happy face for another. Does that feel happy? Okay, we're going to use the vertical line test to see if this is a function or not. So if it only crosses through the graph once, it is a function. Okay? If it crosses through the graph more than once, so boom, boom, it is not a function. And the reason why is because there's more y values, for every x value, there's more than one y value. Okay, so see how the x value would repeat? It's in the same line. Essentially, anytime x repeats, it's not a function. Okay, you can have only one output for every input. Output is your y value, input is your x value. Okay, so let's just take a look at some mappings here. We're mapping A to B, and this one's saying that A is half of B. If we take a look, 1 is mapping to 2, 2 is mapping to 4, 3 to 6, 4 to 8. These are essentially giving us ordered pairs. We're mapping an x and a y together. So we get a 1, 2 is our first ordered pair, 2, 4, 3, 6, 4, 8. Looking at the x coordinates, do any of these x coordinates repeat? So it is a function. Yeah, function. Okay, let's take a look at part 2. A is the square root of b. And if we take a look, we're mapping negative 2 to 4, 2 to 4, negative 3 to 9, 3 to 9. You're saying it's not a function? Okay, let's find out. First of all, a is the square root of b. Does that make sense? Is negative 2 square root of 4? Is 2 square root of 4? Yeah. Negative 3 square root of 9? Yep. Okay, let's map these points. Negative 2 maps to 4. 2 maps to 4. Negative 3 maps to 9. And 3 maps to 9. So for all of you who said it's not a function, take a look at the x coordinates. Do they repeat?
No.
Do they repeat?
It's functional.
Yes. Okay. So none of the x values repeat, which means it's a function. Good job, Ben. All right. So do we have a basic understanding of what a function is or isn't? We haven't really seen a non-example yet, but we will soon. Okay, if the x values don't repeat, we have a function. So the inverse of a function is basically undoing an action. It's kind of like the opposite action. We'll get into a little bit more depth soon. But what do you guys notice about this mapping compared to this mapping? It says A is half of B, B is double A. It's the inverse, it's opposite. Okay, we're undoing this action. If we took half of B, well, B is also double A. What happened to the A and B? They switched places. Very good. Okay, they're exchanged. So let's take a look at the ordered pairs here. 2, 1, 4, 2, 6, 3, 8, 4. Excuse you. What happened to the x and y coordinates. Here we had 1, 2. Now we have 2 to 1. Good. They flipped. They switched places. Hey, let's test if it's a function or not. Any x values repeat? Nope. So this one's still a function. Speaking about inverses again. Okay, let's look at the word description. A is the square root of b. The inverse would be b is the square of a. We're squaring now. Is that true? Is 4 the square of negative 2? Is 4 the square of positive 2? So if I went 2 squared, I would get 4. Yeah. Same with 9, mapping to negative 3. Let's write out the ordered pairs. 4 maps to negative 2. 4 maps to 2. 9 maps to negative 3. And 9 maps to positive 3. Are there more than one output or y value for every x value? Yeah. So we can see x equals 4 has 2 outputs. Therefore, it's not a function. Now, if you feel like circling in below, you can, but we've labeled it already on each mapping, so I think we can skip that. So just reading below here, the domain of the inverse is the range of the original. Does that make sense? Domain is usually all the x values, but now our x values have become our y values on the inverse. Okay, so if this originally was my domain, and now it's over as the y values, it's my inverse's range. So essentially, domain and range switch just like the x and y values switch. Okay, and as you can see, the inverse function, it might not necessarily be a function. It's just a relation. So let's see if you guys can figure this out. So the operation of putting your socks on and then putting your shoes on is described. What would be the inverse of those actions be? If we were to undo those actions. Which would you do first? Good. We take our shoes off first. And then we take our socks off. Would it make sense to take your socks off before you took your shoes off? Probably not. Depends what kind of footwear you have, I suppose, but. Alright, so we have a few more operations here. The function described is given here. We're going to describe the inverse function. What operation would be described? Hey guys? So Stan, we're multiplying by 2. What's the opposite of multiplying by 2? Good. Divide by 2. Hey, what's the opposite of squaring? Square root. And I'm actually just going to bring your guys' attention to the example above, so look in your notes. What did you guys notice? We started with, on set 2, so on this side of the page, we had a is the square of b, and then the inverse was b was the square root. Okay, was that a function or not? Okay, the last example, no, it was not a function. And then the first one was talking about multiplying and dividing. Okay, were those both functions? Yep. Okay, the third part, take the reciprocal. So let's say I started with the function x. If I took the reciprocal, so I'm mapping x to 1 over x, what would be undoing the reciprocal? X over 1? Perfect. And so what is that? What happened to the denominator and numerator? They flipped, so again we took the reciprocal, right? Good job. Okay, and the inverse is x a function? Yeah. Alright, we're dividing by 3, then adding 1. We need to take the inverse, so we're undoing that action. Which means we're going to subtract 1 first. And then we're going to multiply by 3. Good. So if we think about that, let's just write this out. So we have, say we started with x. We had to divide x by 3 and then add 1. If we reverse that, we would then subtract 1 and then we'd multiply by 3. Would we have a function? 3x minus 3? It's a line. If we did a vertical line test, we wouldn't repeat any x values, so again, that's a function. So we already talked about how the ordered pairs x and y switch, and we're just going to put that into action a little bit more here. And because we already talked about it, let's just go down to example number 3. Alright, so in example number 3, we're given a set of ordered pairs here. In order to find the inverse, remember, we switched the x and y coordinates. So up above we have our set of ordered pairs. Our new ordered pairs is just switching the x with the y. So we're going to get -2, -4, -1, -2, 0, -1, 1, 0, 4, 2, 8, 3. What happens to the signs when we switch x and y? Do they change or stay the same? Good, they stayed the same. We don't change the signs of x and y, we just literally switch x and y. So why don't we use one color to graph the points of the original function, and then we'll use another color to graph the points of the inverse. We'll start with -4, -2. We'll do the original set of ordered pairs first. -2, -1. -1, 0, 0, 1, 2, 4, and 3, 8. And I'm just going to draw a line through those points. Crayons? Nice. This is my original function. Now I'm going to plot the points of the inverse function. Okay, so we have -2, -4, -1, -2, 0, -1, 1, 0, 4, 4, 2, and 8, 3. So have you guys ever taken a piece of paper, you painted maybe one side of it, then you folded it over, and then when you open it up you got a butterfly? Have you guys ever done that? It's like an elementary project. But basically, butterflies are perfectly symmetrical and there's a mirror line. Inverses act pretty much the same way. There's a mirror line that the original function will reflect over to show the inverse function. So I want you guys to visualize where that mirror line would be. Any guesses? Anyone want to come up and draw it? Brandon, you think you know it?
The mirror line?
Yeah?
Yeah.
Come on up.
Excellent line. How was this week?
Just say never make eye contact when the teacher has the question.
Mine's slightly out.
Okay, what?
One line is? On mine?
Right through the origin, that's perfect.
That was good, Brandon. That boy.
Good job, Brandon.
Woo!
Well done. The reason why is because this should have been -4, -2. It should have gone there. Thank you. So it's just off on that first one. That looks a little better. Very good. Mirror line. That's awesome. What's the equation of that mirror line? Anyone know? What'd you say?
I just said X, yeah.
Yeah, y equals x.
Oh.
That easy.
Yes.
Hey, we talked about how x and y switch places, so it would make sense that it would reflect across the line y equals x, or about the line y equals x. So our mirror line is y equals x. Beautiful butterfly. So moving on, we're going to practice that. So if we're reflecting the original function about the line y equals x, that basically means we're switching all the x and y coordinates of each point. So if you want, for each graph, you can draw the line y equals x to start. It's going to be my mirror line. And you guys get to be the driver here. There's two different ways that you can draw an inverse. You can literally look at it, and if you're really talented with reflections, you could just figure out, okay, well this is going to be over here, and that's going to reflect down there. Okay, if you can see that, great, but there is an easier way going back to the ordered pairs. So let's just mark out a few of the original ordered pairs. Okay, so this one is, we're going by a scale of 2, so we have -6, 0. This one's 0, -6, and then 6, 0. Like we did in the original example, how do we find the inverse of inverse ordered pairs? What do we do? Nolan? Flip what? Brilliant. Okay, so we get 0, -6, -6, 0, and 0, 6. And then we'll just plot those points. So 0, -6, so it overlaps with the point on the original function. -6, 0, again overlaps, but this last one won't. 0, 6. We're up here. So great, I've drawn 3 points on the graph. Now I kind of have to look at the original function to visualize where it would reflect. Okay, so this has to go about, it's reflecting about that y equals x mirror line. So it's going to be across it. And this is also reflecting over, so we would just connect those two dots. Okay, so you're pretty much just connecting dots. Okay, again for part B, we're going to draw the mirror line. Try and make it as straight as possible, unlike mine. I'd recommend recording a few significant points here. So in red, I'm just highlighting those. First ordered pair I see is -6, 0. At the top we have 0, 4, sorry. And over here we have +6, 0. So like Nolan was telling us, we just switch the x and the y coordinates. We get 0, -6, 4, 0, and 0, 6. Then we plot them, and we connect the dots. Okay, so we have 0, negative 6, 4, 0, 0, 6. I have a question. Does the shape of the graph change and the size? No, the size and the shape stay exactly the same. It's just the orientation, or where it's located in position, that changes. So we're going to connect the dots.